All right, I am back, guys. And today we get back to the good stuff that makes geometry fun. Yes, you all know what I'm talking about. We're going to be doing some proofs. It's been a while since we've done some good geometry proofs that weren't algebraic, but some nice Euclidean two-column statement reason proofs. Ah, can you guys smell that excitement? I can feel it through the computer. Oh, I'm so happy. All right, but before we get to that good stuff, guys, we got to do some definitions, or actually just one definition, which is that of a chord. So what is a chord? Circles, they have chords. So if I draw a circle, that, for example, is a chord. This is a chord. So can anyone tell me the definition of a chord? First, what kind of geometric thing is it? All right, very good, class. It is a line segment. All right, it's a line segment whose endpoints, where do the endpoints of this line segment lie? Very good. Whose endpoints lie or are on the circle. All right. So today we're going to talk about some theorems involving chords. So in this diagram here, let's name the chords. So BA is a chord. Its two endpoints, B and A, are on the circle. And it looks like CA would also have to be a chord for the same reason. Its endpoints C and A are on the circle. So we got BA and CA. Right, chords are line segments, so the notation is just the same as for any other line segment, just a little dash above. And is a diameter a chord? Well, it looks like CA is a diameter. It passes through the center, right? And remember our definition for diameter was just a line segment whose endpoints are on the circle and passes through the center. So the diameter is just a special case of the chord, or a special case of a chord. So yes, is a radius a chord? Well, is OA a chord? No, because one of those endpoints is the center of the circle, right? Not on the circle. So we got a yes, no situation there. And now we are all ready to do some nice theorems. So in this first theorem, it says in a circle or congruent circles, congruent arcs are intersected by congruent chords. So what that is saying is that if these arcs here are congruent, FG and HI, then the chords which make up those arcs also must be congruent. So it's saying HI therefore must be congruent to FG if arc HI is congruent to arc FG. So how are we going to prove that? Well, I want to just show you this in Sketchpad first. So let me switch my screens. All right. So hopefully you guys can see this right now. All right. So what I did in this here is I constructed two congruent arcs. Let me measure the lengths of these arcs right now. So we got arc CB has a length of 8.28 centimeters. And let's measure this arc, arc length. Click the wrong button. DE, measure arc length. There we go. So we got two congruent arcs. And the theorem says if those arcs are congruent, then these chords would also be congruent. So we got chord CB and DE, they're represented by, what is that, L or I? They're represented by I and I prime here, right? They're both 7.58 centimeters. And you can see I can adjust the diameter or the radius of the circle. Doesn't matter, I can make the circle bigger or smaller, right? We see the chords, or sorry, the arc the arcs are still remain congruent. Arc CB is still congruent to arc BE, and our chords are still congruent. I can also adjust the size of the chords, right? And the chords which form the arcs are still remaining congruent. So I've shown it for this case, I can show it for a million different cases, right? But that is not a proof, right? I can't show you every single possible combination. So we will have to do a nice Euclidean proof. And let me go back to sharing my iPad now. And let's take a look at this proof. All right, so what are we trying to prove, first of all? Well, we're trying to prove, well, let's write what we're given first. That's probably smarter. What are we given? We're given, in a circle or congruent circles, congruent arcs. So we're given congruent arcs, right? We're given FG is congruent to HI. FG, right, the arc, so make sure it's the arc symbol, is congruent to arc HI. And given that information, we want to prove the chords which make up those arcs, FG and HI, are congruent. All right, so I'm going to write out the statements and some of the reasons, right? I will speak them out clearly and slowly, so you have plenty of time to write them down. This is a video, so rewatch it as many times as you need. All right, but step one, that's going to be our given. We have these chords are congruent. All right, and that is given. Step two. Well, I don't have a lot here, so we're going to construct something. What do you think we can construct? Right, based on what we did yesterday, we talked about central angles. So maybe, just maybe, constructing these guys might help. So all of those things I just constructed are radii, right? Because they all start from the center and end on the circle. So I'm going to construct radii. And what are these radii? E, H, I, G, and F. Construct radii, EH, EI, EF, and EG. All right, and what is the reason I can use for why I can construct radii? Excellent, very good. Right, between 2 points, only one line segment can be drawn. All right. So step three. Well, clearly all of those radii are congruent. So I can say EH is congruent to EI, is congruent to EF, is congruent to EG. Right, and this is a reason we've done plenty of times, right? Radii of the same circle are all congruent. So there we go. I'm going to get rid of those tick marks. That's what we're trying to prove. And let me use double tick marks here because that was where we started. That was given. All right, so all those radii are congruent. Oh, so I got two triangles, two sides congruent. Can I prove those triangles congruent? Well, here is one of the new reasons we're going to be using, which we saw from Monday's lesson. Was it Monday? No, today's Friday. From Wednesday's lesson, right? So these arcs here are congruent. HI and FG are congruent. Do you remember what that means? Right? If those arcs are congruent, then don't we also know the central angles are congruent? Right? That must mean these angles here are also congruent. And the reason for that is, well, let me write out the statement first. So I am going to say angle HEI is congruent to angle FEG. Let me label them 1 and 2. I'm going to say angle 1 is congruent to angle 2. Right? This is something we saw on Wednesday. And what we saw on Wednesday is that congruent arcs are intercepted by congruent central angles. I think we actually went the other way on Wednesday. We said the converse statement, but of course this is also true. So I think on Wednesday we showed that if we had congruent central angles, then those form congruent arcs. Right, of course, vice versa, that's fine. All right, so congruent arcs are intercepted by congruent central angles. And now I can say those two triangles are congruent, right? Name them by their corresponding parts. So I'm going to say triangle FEG is congruent to triangle HEI, right? And the reason for that is, looks like we got some side angle side action going on here. Oh, some good stuff. All right, it's been a while since we've done this. Doesn't it feel good? All right, side angle side. And I think you guys can finish it up from here, right? Last step. Now that those triangles are congruent, we can use CPCTC, right, to say those chords which form the arcs which were congruent are also congruent. So FG is congruent to HI, and that is CPCTC. All right, so in a circle, congruent arcs are intersected by congruent chords, right? So that's what we mean here. And so we did in a circle. I want to point out to you guys, this also works if we're dealing with two congruent circles, right? If you have two separate circles which are congruent, and we have congruent arcs in these two circles, right? Those chords are also congruent, of course. All right, and down here we have the converse statement. I'm not going to do a full proof of this one, but this says in a circle or congruent circles, congruent chords intersect congruent arcs. So down there, that one is giving you a different given. Instead of giving you the arcs congruent, they're going to give you the chords congruent. And we can do something very similar to prove the arcs congruent, given that the chords are congruent. So I'll just talk through this one. We would do the same construction, drawing all of those radii. Again, all those radii are congruent. And this time we can prove the two triangles congruent, right? This triangle and this triangle, congruent by side, side, side. And then once we prove those triangles congruent, we can say these angles are congruent by CPCTC. And then we would say congruent central angles, right, or intercept congruent arcs, right? So we would use the same statement, except we will switch it around, right? We'll say congruent central angles intercept congruent arcs. So if you want to write that one out, that's the converse theorem. All right, moving on. Next theorem we're going to prove is a diameter perpendicular to a chord bisects the chords and its arcs. A diameter perpendicular to a chord bisects the chord and its arcs. So let me draw a circle. And if I draw a diameter perpendicular to a chord, so let me draw a chord first of all. So I draw a perpendicular to this chord. Like so, right, which is a diameter, so it passes through the center of the circle. And that looks like the center to me. Well, then the chord is going to have, or the chord will be bisected, and its arcs are going to be bisected. All right, So let me show you this on Sketchpad as well. And then we'll go ahead and prove this. So back to Sketchpad. Is that? Click here. All right. And we're in action. All right. So I got a circle. I'm going to draw a chord first. Bam. Click on my chord, click on the center of the circle, and construct a perpendicular. So from there to there. If I hide this, there is my diameter. So what I'm saying is that this diameter is going to bisect this chord. So let me measure this chord and see if its two parts are in fact bisected. So let me measure that distance. AB is 3.6. So if I call from there to there BC, what does that have to be? Also 3.6, right? If I measure this arc, I think it's going to name it D when I click there. So let me measure that arc length. Nope, called it F. So arc length AF is 4.03. So what do you think this arc length FC is going to be? Let me measure that arc length. Also 4.03. So a diameter perpendicular to a chord bisects the chords and its arcs. Or the chord, it should be singular, and its arcs. So why is arcs plural? Well, AF is congruent to FC, but couldn't I also look at this chord and this chord? Wouldn't those also be congruent? Well, let me take a look. If I go from there to there, measure this arc length, the length of arc AG is 11.44. Let's measure this arc length. That is also 11.44. All right, so both sets of arcs are going to be congruent in this case. And of course, I can move any of these points around, right? And look how those numbers stay nice and congruent, right? And again, I can show you an infinite number of examples, but that is no proof, right? Because I can't show you all the examples. So let's do a Euclidean style proof. And get back to my iPad. Share this. Screen mirroring. Mirror. And there we go. All right, so let's write out our givens and what we want to prove. So I'm going to give this some letters. Let's call this circle O. I'm going to call this A over here. Call this point up here B. And let's call this C and D. So I know I'm giving a diameter, BOA. So given diameter, BOA, and I'm given that it's perpendicular to this chord, CD. So given that diameter, and BA is perpendicular to CD. All right, so I can mark this up with a right angle right there. So, you want to prove arcs congruent. So based on our last proof, anytime we want to prove arcs, like CD and BD congruent, well, that's going to involve central angles. And right now, I don't see any central angles, right? So we're going to have to draw those central angles in. So the idea is whenever we want to prove arcs congruent, we're going to prove the central angles congruent because central angles, congruent central angles intersect congruent arcs. So I think it would be smart to construct these radii again, right? So let's just do an analysis. So if you construct these radii, what can we show? We can show this is congruent and that is congruent, right? And I think I can prove these two triangles congruent. So aha, these are all right angles, right? And I think that's going to be reflexive property. So can we use angle, side, side? No, we cannot. You know what that spells. So this is a special case of angle, side, side because it's a right triangle. So aha, that's hypotenuse leg, right? And I think from there you guys can see how to write out this proof, right? But if you want to give it a shot, go ahead and try writing out this proof. When I did it the first time, I got 13 steps. So if you want to try it, go ahead. You should get 13 steps. If you want to follow along now, let's give it a shot. All right, so step 1, I'm going to list out my givens. So copy and paste. All right. And who thought that you would actually be able to copy and paste for one of my tests? But now, yes, you can do that on one of my tests. And the reason for that is given. I'm not going to write out the reasons. All right, you guys write them out. All right, step 2, we're going to construct those two radii, OC and OD. All right, same reason as last time. Between any 2 points, only one line segment can be constructed. All right, we know all radii are congruent. Or radii of the same circle, sorry, are congruent. So that's the reason for step 3. Step 4, well, I said that they are perpendicular, so I know that these are right angles here. I guess I should give this a name also. Let me call that point E. So I know angle CEO is congruent to angle DEO. I'm going to name those 1 and 2 to keep it simple. So angle 1 and angle 2 are congruent, but before you can say they're congruent, you have to say they are right angles. And actually, you don't even need to say they're congruent. Right? They are right angles because perpendicular lines intersect to form right angles. And step 5, this is a step a lot of people forget. I'm writing triangle. What do we have to say about the 2 triangles? We have to say those 2 triangles, triangle CEO and triangle DEO, are right triangles, right? Because I'm setting you guys up to use hypotenuse leg, right? And hyp leg only works in right triangles. So you have to say that these are right triangles. All right, we're going to use reflexive property and say that OE is congruent to OE. All right, so let me mark up my diagram as we have it so far. We said that these radii were congruent. Boom and boom. We said this was reflexive, so that's congruent to itself. And now we have the setup for hypotenuse leg. So again, make sure you're naming the triangles by the corresponding parts. I'm going to copy and paste this and say triangle CEO is congruent to triangle DEO. And the reason for that is hypotenuse leg. We haven't used that in a while, right? That is good stuff. All right, so once we know those triangles are congruent, well, can't we say that, oh, hold up. You know what? I never even wrote what we were trying to prove. All right, so what are we trying to prove? Let's go all the way back here. All right, very, very bad on me. All right, so what are we trying to prove? We're trying to prove, so given a diameter perpendicular to the chord, that it bisects the chords and its arcs. So if it bisects the chords and its arcs, or bisects the chord, that should be singular, right? Our chord CD is bisected, so we're trying to prove CE is congruent to ED. That's our first part. CE is congruent to ED. And we're also trying to prove that the arcs get bisected. So that's arc CD, right? So it gets bisected, which means arc CB is congruent to arc BD. So arc CB is congruent to arc BD. But like we talked about before, you could think of it as bisecting this arc as well, right? So both the minor arc and the major arc get bisected. So we should also really prove that CA is congruent to AD. So arc CA is congruent to arc DA. All right, so now coming back to here, now we can do we can prove one of those things we want to prove. We can prove this guy, CE is congruent to ED. CE is congruent to ED, and that is done by CP/CTC, right? Because we proved those two triangles congruent. So boom, boom, that is proven. Right? We also want to prove these arcs congruent. So let's find the central angles to those arcs. Aha, let's call these angles 3 and 4. Right? Those angles also must be congruent by CP/CTC. So therefore, congruent central angles intersect congruent arcs. So step 9, angle 3 is congruent to angle 4. Right, same reason, CP/CTC. All right, aren't you guys happy? You don't have a regents at the end of the year. So you can write this for the rest of the year. Don't have to worry about writing corresponding parts of congruent triangles are congruent. Lucky you guys, lucky you. All right, so those angles are congruent. So now the arcs are also congruent. This statement I will write out because it's a new one. So we should really say in a circle, right? This is in a single circle. In a circle, congruent central arcs. What am I saying central arcs? Central angles intercept, right? This word intercept is kind of just like creates, right? Creates congruent arcs. But we also got to prove that these arcs are congruent. So I'm going to call these angles 5 and 6. So how can we show angle 5 is congruent to angle 6? Well, I'm going to do something we haven't done in a while, which is angle 3 is supplementary to angle 5, and angle 4 is supplementary to angle 6. Right? And we can say angles that form a linear pair are supplementary for that reasoning, which sets us up for, all right, what's our next statement? We haven't used this one in quite a while, but now we can say angle 5 is congruent to angle 6 for what reason? Very good. You guys remember this one? Supplements, this is step 12. Supplements to congruent angles are congruent. Such a classic. And so finally, you can say arc CA is congruent to arc DA. And the reason is the same as step 10. In a circle, congruent central angles, which we just proved, right? Angles 5 congruent to angle 6, those are central angles. To those two arcs, we prove those congruent, so their intercepted arcs are also congruent. Voila. All right. I don't know how long I've been recording, but we got one more theorem, all right? I'm not going to finish this one up. You guys will be finishing this one up for homework, but I do want to set you guys up for success on this one. So this one says, if two chords of a circle are congruent, then they are equidistant from the center. All right. So Let's start with a circle. And I'm going to draw two chords, which are congruent. And let's all use the same letters. So I'll set this up for you. Those chords don't look congruent, but pretend they are. Actually. All right, pretend those chords are congruent. So if two chords of a circle are congruent, let's say AB and CD, and let's call this circle O, then they are equidistant from the center. So what's the shortest distance from a segment to a point? Aha, very good. Shortest distance is a perpendicular line, like so, right? That's the shortest distance. So we're saying these two chords are equidistant. So what we want to prove is that these two distances are congruent. So let's call this, I don't know, A, B, C, D. Let's call this point E and point F. All right, so here's the setup. We're trying to prove those two lengths are congruent given that AB is congruent to CD. We want to prove EO is congruent to OF. So I'll give you guys a hint, right? We're going to do another construction first. And you can probably guess what we want to construct because we did it in the past two. Right? We're going to construct these two, or these four sets of radii, right? And we know all those radii are congruent, but we're going to be using the theorem that we just proved over here, that a diameter perpendicular to a chord bisects the chord and its arcs. So what we just proved back in the last proof is that a diameter, oh, I forgot, I drew that in myself. What we just proved is, erase all this, right, that a diameter creates two congruent chords if it is perpendicular to a chord, right? But wouldn't this also be true if instead of a diameter we did a radius, right? The same exact property also works for a radius. So this didn't need to say diameter. It could have said a radius perpendicular to a chord bisects the chord and its arcs. So we're going to be using that because guess what? If we extend OE, right, isn't that a radius? Or if we extend it all the way, isn't that a diameter? So we're going to be using that fact to say that these arcs here are also congruent. And we can also say, right, also bisects the chord. So we can also say AE is congruent to EB. So you're going to be using that fact in this proof. And I gave you like the main hook, or the main thing you had to see in this proof. So from there, I think you guys can finish this one up. All right. So I know some of you guys actually do like proofs. So if that's one of you guys, then you're welcome. All right. Let's have some fun. But for the rest of you, this is the good stuff. All right. So I hope you guys have a good weekend. I'll see you guys back on Monday. Take care, stay safe, and see you later. And I forgot, I'm still recording.